Let's prepare on the consolidation of soil. So before going into the topic, let us see what is consolidation means. It is just a compression only, but due to the expulsion of water from the soil. So water, if we are taking out of the soil and compressing it, means we call it as consolidation. If we are removing the air alone from the soil, means we call the term as compaction of soil. Okay, so first at T is equal to 0, that is at initially the effective stress will be what? Normally effective stress is sigma minus U, that is total stress minus pore pressure. Okay, so but here due to the consolidation the sigma will be equal to sigma, so that the initial stress, effective stress will be 0. And then at few minutes what happens means the sigma dash will be equal to sigma minus the pore water pressure. So at that time it will be greater than 0, which is a primary consolidation, and after a long time this pore pressure will be equal to 0, so that sigma dash will be equal to sigma alone, that is the total stress alone. So at that point it is the having a highest value, so that it is the secondary consolidation, and this is due to creep. Creep means it is the sustained load which is given for a very long time. So the secondary consolidation is achieved after a long time only, whereas initial and primary consolidation occurs within a short time. And then we call this term hydrodynamic lag. So this is nothing but it is the delay caused in the consolidation process by the slow drainage of water. So when the water is removed slowly, means there is some lag happening, and we call it as this hydrodynamic lag. And at this time, that is on the consolidation process, automatically the pore pressure will be decreasing, so that the sigma dash, effective stress, will be increasing. Void ratio also will be decreasing, and S remains same. So S is nothing but it is degree of saturation. It always remains same throughout the process. And next we are going to see some terms which are needed to study this consolidation process to find out the settlements and consolidation time and everything extra. Okay, so first term we are going to see is AV. So it is the coefficient of compressibility, and this is nothing but it is a decrease in void ratio per unit increase of pressure. Okay, so AV is equal to minus del E by del sigma dash. Why we are using this minus means we know that the void ratio is decreasing now, so to denote that we are using minus here, and the unit is meter square per kilonewton, because for void ratio there is no unit, and for stress it is kilonewton per meter square. So here the pressure increases means the AV will be automatically decreasing. The next term we are going to see is compression index CC. So here the CC is taken from the slope of the curve. So the curve is nothing but, let us see this graph first. So in the y-axis we will be having the voids ratio, and in the x-axis we will be having log to the base 10 of sigma dash. Okay, so the graph will be like this. So when we take the slope here, it is E1 minus E2 by log to the base 10 of sigma F by sigma 0. Okay, so it's nothing but it's the final and initial effective stress of the graph. So for this, as it is a slope, it is no unit, and there is a simplified formula here. We can directly find the CZ with respect to the liquid limit for the remolded soil and the undisturbed soil. So it is nothing but CC 0. is equal to 0.007 into the liquid limit minus 10%. So the next is for undisturbed soil, it is CC is equal to 0.009 into liquid limit minus 10%. And then the next term is the consolidation settlement, that is the primary consolidation settlement. So here SF is denoted as settlement, which will be equal to del H. So it is equal to del E by 1 plus E naught into H. So it's E naught is the initial voids ratio, and del E means it is the difference between the initial and final void ratio. And here the term MV is used here. So this will be seeing in the next formula. So MV into H into sigma dash, del sigma dash. So this will be a continuation of the next formula. We'll see that. And then it is also denoted as HCC by 1 plus E naught log of sigma dash F by sigma dash 0. Okay, so this is the formula which we will be using for finding the settlement mostly. So they will be giving the initial and final effective stress and the initial voids ratio also, and H they will be giving, that is the height or thickness of the soil something, and CC also they will be giving the value. So with respect to that you can find the settlement easily. The next is coefficient of volume change or volume compressibility. So this is only MV here. So this is nothing but it is change in volume per unit of initial volume due to unit increase in pressure. So change in volume means it is del V per unit of initial volume. So initial volume it is V naught or V due to increase in unit increase in pressure. So here mv is equal to del v by v naught into del sigma dash. So this only is used in the previous formula, and del v by v can also be written as del h by h. So in the same formula they are substituting del h by h instead of del v by v naught, and this is also equal to mv, and the same thing can be substituted by del e by 1 plus e naught also, the same formula. So you can remember like this, del v by v naught or del h by h or del e by 1 plus e naught. And we know that del e by 1 plus e naught is, del e by del sigma dash is AV. That is the first thing we have seen, no? So we can use that coefficient of compressibility here. So AV by 1 plus E naught. So this is also a relation between this volume compressibility and the coefficient of compressibility. And then we are going to see the Tesagi's one-dimensional consolidation theory, because the consolidation process is completely based on this Tesagi's assumptions only. So they take it as the soil is incompressible and the Darcy's law is valid, and consolidation is only in the vertical direction. And then the secondary consolidation is not considered in this Tesagi's assumption. Here AV, MV and K are constant. So AV we know that it is coefficient of compressibility, ME is the coefficient of volume change or volume compressibility, and K is nothing but here the permeability factor is used here, the coefficient of permeability. So the equation goes like this: dou U by dou T is equal to K by gamma W, that is the unit weight of water, into mv into dou square u w by dou z square. So dou U by dou T is equal to CV dou square u by dou z square. So this is the main formula for the Tesagi's consolidation theory. So they may ask this in MCQ, and we know that CV is equal to, this is the relation given here, CV is equal to K by mv into gamma W. Okay, so that is the coefficient of consolidation is directly proportional to the permeability and inversely proportional to the volume compressibility and unit weight of water. So here the unit of K permeability is meter per second, and for MV it is meter square per kilonewton, and unit weight of water kilonewton per meter cube. So that if you cancel everything, the CV unit will be getting us m square per meter square per second, and the dimensional unit can be written as m0 L square T minus 1. So here CV is directly proportional to CC. So this is also important. And then we go to the term time factor or the time of consolidation, that is time taken for the consolidation to happen. So here TV is equal to CVT by D square. So here CV is the coefficient of consolidation and T is nothing but it is the time for consolidation, and D square, D is the depth, that is we are taking the drainage path, no? So if you are taking the single drainage path means you will be taking H alone. If it is a double drainage means you will be taking H by 2. Okay, so this is the formula for time of consolidation. So with everything given we can find the time factor here, and then for the same degree of consolidation TV will be same only. So this is an extra point to be noted. And then from this formula you can see that T is proportional to D square by CV. So if you are taking D square and CV to the next side means you can tell that T is proportional to D square by CV. So that T1 by T2 is equal to D1 by D2 the whole square, that is D1 square by D2 square. So actually what we are coming to tell here is T is nothing but the time taken, and D we know that it is single drainage For drainage purpose it is H, and double drainage it is H by 2. So if you take for example the one is single drainage and 2 is the double drainage, means if we substitute here the H and H by 2 in the D1 and D2, means you will be getting the single drainage is 4 times greater than the double drainage. So you will be getting T1 is equal to 4 into T2, like that you will be getting. So if in a question they are given some time, this is the time taken for the single drainage to happen, then what is the time taken for double drainage, means you can use this relation so that you can easily find the answer. So the longer time is taken by the single drainage, so we know that, and if it is a double drainage means it drains fastly, so it will be 4 times faster than the single drainage. And the next is the TV, that is time factor, depends upon the degree of saturation. So with respect to the degree of saturation also some formula is given here. So if you see here, means when U, that is degree of saturation, is less than or equal to 60%, means TV is equal to pi by 4 the U percentage by 100 the whole square. So you can directly do this. If it is greater than 60%, means 1.781 minus 0.933 log of 100 minus the degree of saturation percentage. And when U is equal to 100, that is the degree of saturation is 100, means the time factor will be infinity. So it takes a very long time for the consolidation to happen. And then it depends on the settlement also. So based on settlement, another formula is given here. The settlement at any time to the final settlement into 100. And the same thing for pore pressure also, it is the settlement initial, the pore pressure initial minus the pore pressure at any time divided by the difference in the pore pressure, that is initial minus final into 100. So these are the formulas to find the TV, that is time factor for consolidation. And then the determination of coefficient of consolidation, that is CV, can be done by some method. So we are going to see that. The first one is the square root of time fitting method. Okay, so this is developed by Mr. Taylor, and the sample of 20 mm thickness is tested with odometer consolidometer, and the graph is plotted with respect to root of T and the dial gauge reading we are getting from the meters. So here only 90% consolidation is occurred or considered here. And the next method is a logarithmic time fitting method, which is developed by Casagrande, and here also they use the odometer only. Here the graph is plotted between the log of T versus the dial gauge. So only this root T and log T differs here, and the consolidation is also 50% is only considered here, whereas in the previous method it is 90%. And then the immediate settlement of the soil. So the immediate settlement of the soil can be directly found by using this formula. So this method, this settlement is independent of the pore water pressure, but it is dependent upon the Q, B, mu, E, I and the influence factor. So here Q is nothing but the net intensity or contact pressure, and B is the least lateral dimension of the area which it is loaded, and mu is the Poisson's ratio, E is the elasticity of the soil, and F is the influence factor. So it depends upon the rigidity or the loaded areas, length and breadth ratio, everything it depends, and the I varies here. So for I, there is a separate tabular column is there for both flexible and rigid soils. So with respect to that, we will be taking the I value. And then the permissible settlement. The permissible settlement for single or isolated RCC footing and for raft foundation they have given separately. So for sand, hard clay and plastic clay they have separately given. So normally it is 50 mm for single clay in sand and 50 mm for hard clay and in single footing, and plastic clay it is 75 mm. So this is for isolated, so it is minimum 50 and maximum 75. But in raft footing, if you see the minimum settlement itself, it is 75 for sand, and hard clay it is 75 mm and plastic clay it is 100 mm, so maximum 100. The next is overconsolidated ratio. OCR is equal to sigma past by sigma present. So it is the stress which is in the past and the stress at present of the soil. So if it is greater than 1, that means the past it has more stress, means it is clearly known that it is overconsolidated and the past pressure is high. and if it is equal to the past pressure means it will be equal to 1 normally consolidated soil, and if it is less than 1 means it is under consolidated soil and has not been consolidated. So this OCC, that is over consolidation, occurs when means if there is a historical structure prevailed there, or if any ice glaciers or sand dunes are present there, if capillary rise is present in the soil and lowering down of water table. And the secondary consolidation, so we already saw that the secondary consolidation takes a very long time and it is difficult to find that, and the consolidation theory formulas also, it is based on the primary consolidation only, because this is due to the creep, that is the sustained load for longer time, and it is a time dependent and it is the function of log of time. So the graph is taken as E and E versus log t, and this is developed by Mr. Letz. So he has given a formula for the settlement of secondary consolidation. It is H C infinity by 1 plus EF log of T2 by T1. So this is the influence factor for various shape and the soil. So here this circle in center of flexible and rigid soil, these are very important values because they generally ask these questions repeatedly. So you can learn all these influence factor, but it is very important to remember these two, that is circle at center of flexible it is 1, and circle at the average of flexible is 0.85, and circle at rigid soil is 0.8. Thank you and keep watching for the next lecture on compaction of soil.